All right, well, welcome everyone to our session today. My name is Bill Magro. I'm from Intel. I'm Intel's Chief Technologist for High Performance Computing, and I also lead our HPC cloud efforts. And I'm fortunate to be joined today by a couple colleagues who've been working with some of our customers, Stefan Saselski from Maxar and Mike Warren from Descartes Labs. Stefan leads a Cirrus Project at Maxar, which is looking at how to do some large-scale weather modeling and building innovative business models around that. Mike is a co-founder, a longtime HPC person, came out of the National Labs, Department of Energy, working on some of the world's largest supercomputers, and he and his colleagues have taken that expertise, applied innovation in the cloud, and are creating incredible new products, information products, working with the cloud around geospatial data. So our focus today is really around the technologies that are enabling this, and then how they're being applied to do global scale predictive intelligence, which creates business value. So our agenda is I'm going to talk a little bit about Intel and how we work with Amazon and how we see HPC, definition of HPC, how cloud fits, where it fits, and how that is changing over time. And then we're going to move to Stefan, who's going to talk a lot about what Maxar's been doing. And then finally, Mike will wrap it up, showing us some of the cool things that Descartes Labs is doing. And we're going to aim to keep some time available at the end for questions and answers. So if you have questions, queue them up as you go, and we'll be happy to take them at the end. So to get started, before you talk about HPC and cloud, I think we all know what cloud is, but you have to define HPC. And traditionally, a lot of folks have thought of HPC or high-performance computing in terms of infrastructure. But at Intel, the way we define HPC is against really three criteria. It's like a problem or an activity that meets three criteria. And the first one is that the purpose of the activity is insight. We're not doing transaction processing. We're not routing packets. The reason we're doing the computing is to actually gain an insight. We want to learn something. We want to know what the weather's going to be like tomorrow with some confidence. We want to know if a certain airplane is going to fly before we build it, right? The product is insight or intelligence, knowledge. The second thing is it has to be computationally demanding. If it's not computationally demanding, how could we legitimately call it high-performance computing? You know, it would be low-performance computing or just computing. And the last one, and I think this is really important, is that when you appropriately and intelligently apply more resources to the problem, you get a more valuable result. So think about a weather forecast. If you do a weather forecast and you have a 16-hour weather forecast, but it takes 48 hours to compute, its value is literally zero. And you can run a weather forecast on your phone. You know, the phone I'm carrying today is more powerful than the Cray that I started working on in HPC, excuse me, in the late 80s. But it won't create value for me in a weather forecast. So if I appropriately apply more resources and I can now get that weather forecast in an hour, it's incredibly valuable. And you can apply that same kind of thinking across anything from precision, rollover calculations, in car crash simulation, rollover simulations, any number of areas that applying more resources gives you higher fidelity, higher confidence, or a faster time to result, better product. And so when you put these three things together, this is our definition of HPC. And that begs the question then of, well, where's the infrastructure? We don't define HPC in terms of infrastructure. And as soon as you free yourself of thinking of HPC in terms of infrastructure, you stop thinking of HPC as being confined to supercomputers. So there's three big trends underway in the way HPC is evolving right now. One is the scope of problems. Traditionally, we've talked about simulation and modeling. People are now thinking about analytics. They're thinking about machine learning. And if you look at them, they meet the criteria I just described. The second thing is scale. There is no end to the path that we're on with supercomputing, solving the largest problems of science and national security and economic security. That's not going away. But the third big trend, and the one that doesn't get talked about as much, is the fact that cloud is disrupting the way HPC is getting done, and it is becoming a legitimate delivery mechanism for HPC. And that's what we're here to talk about today. So one of the questions that comes up is what workloads really can run in the cloud and which can't. And there's a couple criteria that people often think about. if we set aside data movement, which I think is a challenge for everyone for the moment, it really comes down to two things. Is the application what we would traditionally call a strong scaled application, meaning I want to apply those more resources, I want to get an answer faster while holding the problem constant. At some point, your efficiencies fall off. And traditionally in the cloud, the efficiencies fell off faster than a dedicated supercomputer. But new technologies are coming out, and we've been working with Amazon to drive some new technologies to actually change that. And I'll tell you about that. The second dimension is how comfortable are you putting your data or your problem in the cloud? You may have regulatory constraints. You may just have concerns and feel safer if your data is on-prem. But if you look at the security certifications that exist with AWS and the track record with security compared to a lot of on-premise large corporations that have been in the news, people are getting more and more comfortable with the concept that their data is just as safe or safer in the cloud than it was on-premise. And so what workloads fit for the cloud is going to be very specific to your situation, but I think everyone can agree that the scope of workloads is growing. And in fact, today we're going to talk about a couple examples of workloads that in the past you wouldn't have thought were possible on the cloud, or you might have thought were not even possible without the cloud, in the case of Descartes. So if you look at what is Intel doing with Amazon on this front to move the frontier, the first thing is we're focusing on workload optimized performance. We have features that exist in our processors like deep learning boosts that allow you to do inference on the fly without having to move the data. That's critical if you want to bring HPC, simulation modeling, and AI inferencing together. We can't be shipping the data off to a remote specialized inference engine. Things like AVX512 power vectorized code, which exists and has existed in high-performance computing for a long time. And something like Elastic Fabric Adapter. I think folks are familiar with the ENA, Elastic Network Adapter. EFA, which was introduced a year ago with the C5n instances, actually brings native messaging capability tailored to HPC applications into C5n and related instances based on Intel Xeon processors. And you're going to hear about the impact of EFA in conjunction with the tuning that Intel's done with Amazon all the way from the lowest level up through the MPI and the application layer, and the impact that that's having on actual results and business results, making workloads feasible to run in the cloud that weren't in the past. So Intel's working across all these areas to make the cloud more capable for HPC in conjunction with AWS. And today we're going to get to see some examples of that. Some of the specific new instance types that are out there, I mentioned the C5n. This was introduced about a year ago, I believe, at reInvent. And it brought a couple things. It brought the latest Intel Xeon processors, of course, but it also brought a more balanced design and higher memory capacity and memory bandwidth, which is very important for high-performance computing applications. We saw a large performance boost from that. It brought 100 gigabit networking and this EFA capability, Elastic Fabric Adapter, which natively runs the Open Fabrics interfaces, which in turn works with MPI implementations like Intel MPI, used by a wide range of codes out there. High memory instances, very important if you want to ingest large amounts of data and hold that, but you don't need it across your entire computation. The high memory instances are allowing people to ingest data, do the pre-processing, do the post-processing, without having to ask for more compute than is needed to get the memory you need. And then finally, the Z1D instances. This was also driven specifically by HPC requirements because there are certain applications where the best technical solution or lowest cost solution, if you just look at the computing, might be to go really broad parallel with perhaps more but slower cores. But when you bring software licensing into the picture, it changes the economics. And in certain industries, per core licensing actually dominates the compute cost. So by having the highest available performance per core, you're actually able to get lower total cost per job. And so these extremely high performance Z1D instances that can go up to 4 gigahertz sustained all turbo performance are critical for delivering value in some of these workloads, such as EDA. So here are a few proof points, just some of the measurements of why you should be looking at moving to the latest instances. It's a better value, it's higher performance, it brings new capabilities. But with that, I really want to spend most of our time today with our partners and letting them tell you what it means in terms of real results that are delivered. So I'd like to invite Stefan up from Maxar, and he'll tell you about the work they've been doing on weather modeling. Hey, Stefan.
All right, so running HPC in the cloud for NWP, numerical weather prediction. We've been doing this now for about 6, 7 months, and it's been really exciting, a lot of challenges, but we've gotten to a really cool place from a results standpoint, and I'm excited to share that with you. First of all, what is numerical weather prediction? It is a really difficult problem to actually solve. If you listen to the keynote Monday night, he just basically tackled this problem and said, no one can really do this well in the cloud, yet here we are today actually doing it. So it's the process of predicting future atmospheric states. There's all these physical equations that govern the atmosphere. You can put that into math. You can code that math into Fortran, and that's what we use. And you compile that, and you can run it really fast on bare metal. Several different agencies run weather models. NOAA has their American model. If you've ever listened to people on TV predicting the weather, telling you, oh, well, the American model or the GFS is saying this, and then they might also say, hey, the European model or the ECMWF or Euro is saying that. There's all different types of models. Many different agencies run it, and we're just actually trying to tackle one of them, which is NOAA's GFS. So the project we named Cirrus Cloud, High Cloud, is the project for running this numerical weather prediction in the cloud. We had 3 main goals. The first goal is actually to take the American model, this FVZGFS. It's got a really long name, not going to say it. And we're going to run it faster than what NOAA does. Why? Because we have clients who, if we can give them that forecast faster, get an edge in terms of whether it's commodity trading, whether it's hater response. I can prepare if I see this disaster first. And we're going to do this through custom output, deliver data through APIs, maps that show hot, cold are here and there, and give them this faster so then they can make those decisions faster. The second goal is we have to make this forecast actually highly correlated. We can't just deliver any forecast. It has to be what NOAA delivers, or as close as we can. Now, that's actually really difficult because there's random number generators in this Fortran code. So actually reproducing that is a real challenge, and we've gotten close, but we're trying to get as close as we can to NOAA. And then, obviously, we're going to leverage cloud HPC for this. We want to use AWS, use the Intel libraries, and build this system that can produce and deliver this forecast faster to our clients, all cloud native. And so what does this look like from a technical standpoint? Well, first, let's look at the workflow. We have a fully serverless automated workflow within AWS. It's all Lambda functions, step functions, and a variety of CloudFormation stacks that build these HPC clusters up in Amazon, run the forecast, and then tear themselves down. Nothing's kept each day other than the VPCs, the networking, the behind-the-scenes stuff like that. Everything is built. We run it for an hour, and we spin everything down. There's a piece that's actually really, really cool, and we can spend another 45 minutes talking about it, which is downloading data, in which we need to get all of this starting point data from NOAA to run their model really quickly. It's a lot of data. It's like 16 gigs of data. They post it, and we're already behind the curve, right? Because we have to get that data, pre-process it, and then start our model. Well, getting that data is actually a real big battle, so we've had to build some really intuitive and scalable solutions to actually get that data in. What does the cloud HPC cluster look like? So we have 2 clusters. We got one in US East 1 and one in US West 2. We use parallel cluster, which is open source. The AWS's used to be open source C5n. Amazon took it, ran with it, and built this really awesome software suite to help you manage clusters in the cloud. And this will build your auto-scaling groups for you, as you can see in the diagram. It will make the head nodes for you, attach a job scheduler for you. We're using Slurm. And it will even mount a FSX Lustre file system for you. We're currently running 156 C5n 18X within an auto-scaling group. This has a 14 terabyte Lustre, and we're leveraging the EFA that we've also heard about at the probably several talks and at the Monday night keynote again, and how that is actually enabling a lot of these big HPC applications to get to where they can be proficient in the cloud. So you have to first lift and shift this huge Fortran-based code into Amazon and then compile it. So we've been leveraging Intel Parallel Studio XE 2019 to do this. And we chose this for a few reasons. The first is, well, we can then leverage the advanced vectorization suite, the AVX512 instruction set. And we can then work with other optimizations where the tightly coupled EFA to Intel MPI, so on and so forth, really are useful for us. So we can actually take advantage of those and run this as fast as we can, while also still conforming to what NOAA has in terms of their optimizations. There's a lot of underlying packages, over 20. They all have to be recompiled and compiled anytime there's updates for, say, Intel, or if NOAA makes a change. So building out this environment has really kind of helped us stay up with the latest and greatest and really optimize this code for the cloud. And what's really interesting about this model, this application, the FVZGFS, is that it's MPI-based. And it doesn't really fit the pets versus cattle paradigm. If one thread of this application goes down, we lose the whole application. So if an instance, a C5n 18X large, fails its health checks, it's done. And figuring out ways to actually checkpoint these applications so that they can be started if that was to happen is really kind of the critical next step in our pipeline of trying to figure that out. Because if we're not faster than NOAA and we lose an instance, what do? It's dead. So the cluster goes down, and we move on to the next run, which is the next day. What does performance look like in the cloud? Using, AWS's C5n 18X instances, Intel MPI with the EFA coupling. We have, as I mentioned, we have the production cluster that we have, and the backup. Our production cluster uses about 5,600 cores, all working on the same task, right? So they're all doing the same thing. It has the 100 gigabit interconnect, and it can complete a 16-day NOAA forecast. That's how long NOAA runs their forecast for, in about 40 to 42 minutes. It varies because of the weather of the day, believe it or not. More weather one day, it actually takes a little bit longer. A little less weather the next day, might not take as long. And our backup cluster, which actually is C5 instances, that's actually used to be our production cluster, and I'll get into that a bit later. But we can do the same forecast in about 48 minutes. The key difference there is the 25 gigabit interconnect. It really actually is inefficient, and you can actually see the difference, tangible results here of how EFA and that tight coupling with Intel MPI works to really reducing the wall clock time. And for comparison, I'll throw NOAA up there. NOAA runs that forecast in about 100 minutes. They use a lot less cores, but they're spread out amongst a fair amount of instances. Their MPI threads are a lot higher than ours. So as I alluded to, we did a lot of proof of concept testing with several teams at Amazon because we were reaching hardware limits on the C5 large instance. There's a packet per second limit. That's 3.25 million packets per second. We were exceeding that and dropping packets. What's the solution? Switching to C5n with or without EFA. Ideally, we're using EFA. And we did a series of tests. Test 0 that I show here was our production cluster. That was that big one, 234 C5 18X instances all working together to make that 16-day forecast. Then we said, well, let's throw in EFA. Let's switch to C5 and 18X. Get them all in the same placement group. That's key. They all have to be in the same placement group to leverage this interconnect. And let's do these tests again. And that's how we got to our production run, which is test number 4 here. And that ran in the 41 minutes. And then if we wanted to, we said, well, let's try using 234 C5n 18X. And we could run the model in just over 30 minutes. Another key thing to note is this model has to initialize first, right? It's got to read in all this weather data from all over the world to do this. And that usually took anywhere between 2 and 3 minutes to do on C5 instances because they're all working together to read that in, gather it, and then send it back out. When you put in EFA in the C5n instances, we saw a 93% reduction in that initialization step, which is crazy. Took it to 10 seconds, 11 seconds from a couple minutes. And so really, what we see here is we just saved ourselves a ton of money using C5n 18X and EFA. We reduced our number of instances by 33%, and we still ran over 20% faster. And we could run even faster if we wanted to. What does this all mean? Well, we produced a similar forecast to NOAA. I didn't show it here, but we're running daily spatial correlations on all this data that we produce, comparing it to NOAA's data to make sure that what we're giving and delivering our clients is acceptable information that they can make actions off of. We cut the computational time versus NOAA by 50%, and we expect to actually just to continue this reduction in wall clock time. Technology is advancing in this space so quickly that once new instances come out, EFA becomes better, we can actually then just switch them in, leverage them, scale up our clusters, and run even faster than we are right now. And it's a lot cheaper. I don't have to manage a bare metal cluster anymore. It comes up once per day, does its thing, tears down, and I'm done. I don't incur any more costs for it, and I'm delivering pretty much the same result as I would if I had my bare metal cluster. It wasn't easy. As I mentioned earlier, there was a lot of difficulty with certain aspects of the project. But we're working towards making this application more fault tolerant. That pets versus cattle thing is critical for us. You have to make the application more fault tolerant. Is that internal checkpointing, MPI-based checkpointing, job scheduler checkpointing? I don't know. We're testing all these right now, but it's a very difficult thing to try to figure out because it takes a lot of data to write out to actually checkpoint an application this big. 156 instances all writing out information that's gigabytes, if not tens of gigabytes, just to start it back up. And when time is critical, like in our application and our use case, checkpointing is very difficult to implement. And believe it or not, we did encounter on-demand capacity issues. We all need these 156 or 234 instances in the same placement group to leverage the really fast interconnect, and so everything can communicate well together. And getting all of that, it can be difficult at times. We're not the only ones sitting in US East 1 running something, or one of the availability zones. There's all you guys too. And that leads to the last point, which is we need to fail fast and recover faster. Doing advanced monitoring, knowing when that node goes down before, the application fails even, if we can get like a signal that just says this node is going unhealthy even faster, that could really save our run and save our application and could still produce the output for our clients. So we're working on just really enhanced network, CloudWatch monitoring and alerting, node-based, MPI-based, integrating with the parallel cluster team on figuring out better ways to do this. There's so many different avenues we can go down to fail fast and recover faster. And so wrapping up, global NWP can be done at scale in AWS, Cloud HPC. It's made possible by all the greatest offerings from both AWS and Intel. I'll say it again, the Intel MPI, the integration with EFA, AWS's C5n 18x instances. We're running 33% faster than we were 3-4 months ago, and we're running 20% faster than we were 3 months ago on 33% less instances. And we're actually just getting started. This model can be run not just once per day. It can be run 2, 3, 4 times per day. There's different models, as I've mentioned earlier. There's different ways we can approach this, and we're looking forward to working with Amazon and Intel to tackle that journey and see where we can go from here. And this all leads to right back to our clients in delivering that forecast faster to them. It enables them to make those decisions faster, prepare, and it makes for better Earth intelligence for our world and especially our clients. And with that, I will pass this on to Mike from Descartes. Okay. Yeah.
Well, I'd like to start with a little background on myself to kind of put the journey I've been on in context, because it's really a journey that is very relevant to what's happening right now in the cloud. So you can see the cover there of Linux Journal. That was back in 1996. Had this idea that we could put together a cluster of servers, connect it with the dedicated high-performance network, and turn it into a supercomputer. And I can say that now and no one laughs. But saying that in 1996, you'd be laughed out of the room. That's a toy. That will never be useful for anything. But that insight that commodity hardware and networking was a key to scalability and parallel computing was really the start of what became what was formerly the domain of special purpose Cray vector supercomputers, became highly distributed memory parallel supercomputers, and after that started being built into a lot of the infrastructure in the cloud. And now you can see that infrastructure coming back together because underneath it's all the same microprocessors and networking. So in 1997, we won a Gordon Bell Prize. So that's a prize given every year for the most significant scientific application run at the highest speed on a supercomputer. So we won that performance prize on the ASCII Red system, which was about 9,000 Intel Pentium Pro processors in Albuquerque, New Mexico at Sandia National Laboratory. Back in those days, they also offered a Gordon Bell Price Performance Prize, where you got the most performance per dollar. Since then, I guess they've decided that if you're worried about cost, it's not really a supercomputer, so they got rid of that part of the prize. But we won that price performance prize with that 16-node cluster shown on the Linux journal cover, which used exactly the same processor, a 200 megahertz Pentium Pro. So that was a big realization. Later on, in 1998, we ran a LINPACK benchmark on our next generation machine, which turned out to be the very first machine on the top 500 supercomputers list that ran Linux. Guess how many of them run Linux today? Every single one of the 500. And it took about 20 years for that transition to happen, but we knew at the time we were onto something. So kind of taking that knowledge and the power of computing and parallel computing, it was actually 5 years ago this week, it was the birth of Descartes Labs. So the co-founders spun some technology out of Los Alamos National Lab. We had 6 co-founders. Over the past 5 years, we've grown to 110 people, pulling together decades of experience in both applications, DevOps, software engineering, and basically creating a company that can combine the power of high-performance computing and the just tremendous flood of data that's coming from all aspects of our world. So HPC powers what we've called a data refinery. Crude oil isn't really valuable for anything as it comes out of the ground. You need to refine it into various products. And data is much the same way. So a lot of the data coming from satellites every day, aerial imagery, it's all sorts of different formats, different sorts of noise. A lot of cleaning needs to happen on that data, and it needs to be normalized so that you as a software engineer don't have to deal with 20 different types of data. You can access these pixels with the same API regardless of the instrument where it was collected or its resolution and so forth. So it's a combination of scalable computing, task scheduling, HPC built on top of a tremendous catalog of data. So every day we have about 10 terabytes of data flow into our system. Data that did not exist yesterday. It's real-time observations of our planet. And that data is ingested and refined and then made available through our platform to build models of the world, both by our own internal data scientists and our customers who use our platform. So this is kind of the connector between the old school way of starting an MPI job where you need a hosts file with the addresses of all the machines, and the world of the cloud where we need to actually talk to an API to allocate all of these resources. So I like simple solutions, and this is a very simple API where you can kind of set up the instances and number of nodes you want, make a Python call, and then sort that data into a file. And an additional trick on this is we mount a shared file system in the image for each of these nodes, and when it becomes alive, it just touches its host name in that file system. So a script on the front end can then determine the instant each of those nodes has become aware and on the network, and then we can start that job without any sort of complicated process. And it actually happens before the API here certifies all those nodes as ready. So this is an example kind of connecting some of that work that we did at Los Alamos in the mid-90s on these, the very first clusters, and what's possible now in AWS with the very latest hardware and networking technology. So if you're not familiar with the NAS parallel benchmarks, they're a set of MPI codes that was written in the 90s to kind of evaluate different aspects of the architectures. So they're given two-letter names like FT for Fourier transform or BT for block tridiagonal. But in 1996, on 16 processors, you could expect performance of hundreds of megaflops. By 1998, that number was now the thousands of megaflops, 2 or 3 gigaflops. Our cluster that we built in 2003, which was still single processor, single core Intel hardware, but now rather than 200 megahertz, the clock cycle was 2.53 gigahertz. 256 of those could get you 60 or 80 gigaflops of performance. Now, in the present day of 2019, you can take one single C5 18x large instance, and that exact same MPI code is running at speeds exceeding the size of these supercomputers from the early 2000s. So I'll use an example there, 104 gigaflops on a single node. And then when you go beyond that to node level parallelism, you're getting up to tens of millions of megaflops, so multiple teraflops. And if you look at the class column there, that's related to the size of the problem that's being attacked. So a class B problem was as big as we could calculate on 16 nodes in 1996. For A, B, and C, the problems got factors of 4 larger each time. But progress was so fast, they decided they needed to make bigger jumps. So C to D was a factor of 16, the same D to E, and then E to F. So these problems that we're running in AWS, just as a benchmark, are 65,000 times larger than those problems from 1996, which were the biggest problems we could run at the time with the resources we had in our group. So if you want a supercomputer, you have to run the LINPACK benchmark. This is a comparison between C5n and C5, which counterintuitively is actually faster on the C5 nodes with TCP. As you look in the details, exactly how the message latency works is code dependent. But there's also very rapid progress is being made on the EFA drivers, which have been around for much less time. So this may already be out of date in terms of the performance. But that's by way of introduction of something we did in the spring, which got a lot of press, which was we spun up about 1,200 C5 nodes on a Sunday. We didn't let AWS know, and we ran LINPACK for 9,200 seconds and got a performance of 1.9 petaflops. So essentially, anyone with a credit card and a few $1,000s to spend now has access to a multi-petaflop supercomputer. So bringing it back to the mission of Descartes Labs and how we're applying technology to geospatial data, this is a demo that you can try out yourself if you go to search.descarteslabs.com. It's called Geovisual Search, where we took an image of the entire planet Earth and cut it into billions of small images, and then ran a convolutional neural network to pick features out of each of those images. And after doing that, you can search for neighbors in this feature space. And by doing that, it's a form of unsupervised learning where, in this example, if you click a box over a football field, in a matter of less than a second, we can search the entire United States at 1 meter resolution to find any image chips that look like what you clicked on. And you can see there the roughly 1,000 closest matches to that image has found any number of football stadium. An analytics problem related to that, which has quite a lot of economic value, is how do we find these large oil storage tanks over the surface of the Earth? So if we do that same sort of geovisual search, you can see here that we found some of these tanks in this particular area, but we certainly didn't find all of them. So we need to refine the code and algorithm that we're using to be more focused on this particular problem. So just kind of as an example of tying our data platform into the ability of our customers who have smart ideas and the ability to apply their own knowledge, we developed kind of this simple computer vision application, which is not a neural network, but uses a template to find circles on the surface of the Earth. So this is only 100 lines of code or so, and we've wrapped the C to do all of the heavy lifting here in Python, so it integrates nicely with our platform. But the magic here is really in some of this Python code, which is using the Descartes Labs API, where you see that dl.raster.nd array is taking an image of the surface of the Earth and bringing it in to a NumPy array, which you can then operate on with any number of packages and applications. So our platform allows us over dozens of instruments to address these pixels, some of which go back to the 70s with the Landsat program. If you tell us a place and a time, we can serve you those pixels on the order of less than 100 microseconds from that request over a multi-petabyte archive. So this is the inner loop of the template finder. And what I wanted to show you is, I think, processors over the last 15 years have not gotten faster from clock frequency like they did in the 1990s. They've gotten faster through AVX and making the vectors wider and wider. And one of the very nice things about AVX is you can address it very nicely using vector intrinsics in GCC. So we can actually declare these variables as vectors and add and subtract and multiply them. So suddenly, between the last page of code and this page, if you're using AVX on a modern processor, you just got a factor of 16 improvement in floating point performance. So this is a result of finding tanks with that object finder. And because of the explicit vector instructions there, this executes at very high speed on Skylake and Cascade Lake processors. And as we go to the next generation of Intel processors with AVX, that code doesn't have to be modified. It will still continue to improve performance. And that, is really an important thing to keep in mind. As we improve the hardware, oftentimes it's at the expense of breaking well-established APIs. So things like the NAS parallel benchmarks were written in MPI, which is highly portable, but no one has bothered to take those benchmarks and port them to use GPUs of any form. It takes a lot of people expertise and time to rewrite code if the underlying APIs have been broken. So really a magic part of HPC in the cloud is these applications that were written 10 years ago with millions of dollars of investment are suddenly not only hundreds of times faster, but are immediately applicable with resources that are easily available in the cloud. So if you'd like to know more about what I've talked about, we've got a couple of technical papers. You can visit our blog or our website. And at this point, I think we have time for questions, so I'd like to bring Stefan and Bill back to the stage, and thank you all for your attention.